Hello everybody, in this lecture we will be solving 1988 IMO problem number 2. Here is a view of this problem. This is a combo problem. As I read through the problem, I will come up with a notation on this side, on this space, so that we are trying to understand this problem because there's quite a few words going on here. So we're given, so n being a positive integer, let a sub 1, a sub 2 all the way to a sub 2n plus 1 be all subsets of the big set B, and then we are also assuming three things. First, each AI has 2n elements for all I. Okay. Secondly, property B, each AI and AJ together, they have only one common element, right? So for I not equal to j, I not equal to j. Okay, and finally this condition, which is this weird one, every element of B belongs to at least two of the AI. B in B, right, belongs to at least two AIs, A sub i's. Okay, so we can solve this problem in two steps, I guess. But the first step is this at least business is kind of worrisome. So I have the following claim. So I claim, and I call it C prime. This is the new statement. I claim the stronger condition still holds, namely that each each B in B belongs to exactly, so that's important, exactly two AIs, two A sub i's. So that condition is a stronger condition, but it is necessary. It significantly simplifies the problem. So let's try to first prove this claim, prove, and then we can try to interpret all these three conditions with the help of graphs, basically, graph theory. And so we're just going to draw some picture, basically. But okay, so let's assume to the contrary. Assume to the contrary that there exists an element x sub 0 in B such that x sub 0 is an element of A sub k. Similarly, x sub 0 is an element of A sub L, and x sub 0 is an element of A sub M. So it belongs to three sets, not only two. So let's see if we can find a contradiction from here. So what I will do is, from our index set, so we have 2n plus 1 subsets, right? So from our index set, I will just remove M, the last one, right? So consider this set then. Our M is a new index set, except that one of the indexes have been removed all the way to 2n plus 1. So please consider this set. This set has obviously has 2n elements in it, and to each for each j in M, I will assign the element of again, so for each j in M, we will assign the element of A sub M that belongs also to A sub j. So what I'm meaning is the following. So consider these indices. Each index is associated with, let's say, so this one is related to A1. Please think of A2 here, and so on. A sub M minus 1, A sub M plus 1, and finally a sub 2n plus 1. Each of these sets share one common element with the set a sub m, right? With the set a sub m. How do I know it? By condition B. By condition B, I know that each of these sets share one element, and let's call this element as g of j in this case. So for instance, let's call g of 1 as the element in the intersection of a1 and am, and I'm going to so in a similar way, so for instance for this guy, so let's call g of 2 as the intersection of a2 and am, and so on, right? So in this case we can assign g of the number in the intersection is g of 2n plus 1, and that's simply the intersection of the sets a2n plus 1 and am, and I know there is exactly one such element there because so therefore what I did here is I created this new set g1 g2 g2n plus 1, right? This set has 2n elements in it, so that has 2n elements in it, and if we focus also closely, we would just realize that, for example, given this, so that's where we try to find the contradiction, right? So g of k as a result would simply be equal to x0, as is g of l. That's also equal to x0. Why? Because this is simply the intersection of ak and am, and this is also the intersection of al. So al and am. But then, okay, so then this should give us the desired contradiction for the following reason. So our function g maps the elements, the 2n elements of the set m, onto the whole of a sub m, right? Because a sub m has 2n elements by condition a, right? So this is crucial. So g maps the elements of m onto a sub m, so this is onto where both m and a sub m is equal to 2n. As a result, g is 1 1. But then this contradicts the fact that what we got here was g of k is equal to g of l, but that's a contradiction because so this is a contradiction because k not equal to l, or you can say if g of k is equal to g of l, if by the 1 by 1 1 it must have been that k is equal to l, but it's certainly not the case. K and l are different indexes. So this therefore proves this stronger condition. So therefore from here on we will assume conditions A, B, and C prime holds, right? So let's write them down. A, B, and C prime are the new conditions that basically hold. Now at that occasion we can identify each of the elements, identify elements of B, because each element of B now can be associated with a pair, an unordered pair. Elements of B, elements B of B with ij, where such that such that B is simply, or you can say it like this: B is simply the intersection of AI and AJ, because only two, so each two subsets, AI and AJ, they have one element in intersection, and that one element is only contained by those two intersections. That's it. No other, no third set or fourth set whatsoever. That's the one. So therefore it is, so this gives us a natural bijection between the set, the elements B in B and the pair AI, AJ, right, of subsets. So at this point, we can now consider a graph theoretical interpretation. Now let's start by considering, for example, a regular pentagon. If we consider the pentagon A1, A2, A3, the subsets A sub i's can be represented as the vertices of this pentagon, and the edges that connect those vertices are simply the elements of B in that sense, right? So you have all these elements of B. Okay, so now the concern is, for instance, each so when you read the problem again, so let's go back to the problem statement, this weird statement. Now it's time to tackle this statement. So for each for which values of n can one assign to every element of B one of the numbers 0 and 1 in such a way that AI has 0 assigned to exactly n of its elements. So what it means is, so the elements in AI, obviously, for instance, let's start with A sub 1. The elements of A sub 1 are the edges emanating from, or and the segments emanating from vertex A1, right? So is that clear, right? So what I did here is, so once we labeled the vertices of our polygon as the subsets of B, the subsets A sub i's of B, then the lines connecting those vertices represent the unique element in the intersection of these sets, for instance. So because we earlier realized that there is this nice association, we can identify each element B in B with a pair of subsets. So therefore, if the vertices are represented by vertices of this polygon are represented by if those subsets are represented by the vertices of this polygon, then the lines connecting those two vertices are simply the elements of B. Well, of B such that they are in the intersection of those two sets. For instance, this line here would simply represent the element, let's call it X, which is in the intersection of A1 and A5. We know there's only a single one, and that's the one, and so on. Okay, so now the problem statement basically is telling us that from each vertex, our set, in this case, for instance, A1 has 4 elements in it, because there are 4 lines going out to the other vertices, to the other subsets, and each subset has one shared element with the other subset. That's why you have only one line connecting 2 points. So the thing is, we need to assign, in this, for instance, particular example, we have 4 lines coming out of A1. 2 of them should be assigned the value 0, and 2 of them should be assigned the value 1. And can we do it for all the vertices? So instead of assigning values 0 and 1, we can probably think of something easier, basically coloring, right? So for instance, if I use a yellow color, I claim this coloring might work after some trial and error, and if you would like, you can pause the video here and try to see if you can color it such that from each vertex 2 of the same colors will come out. But it turns out this coloring scheme works. So if you color the edges of our polygon, or in this case a pentagon, then the other so let's do it. Then the remaining portions, let's do it this color, and I claim this works. And it's no surprise, so obviously we have 2 yellows and 2 greens coming out of A1, similarly from A2 and so on. So this scheme worked. But does it always work? This particular example was 2n plus 1 is equal to 5, suggesting n is equal to 2. For instance, would it work? Can we come up with a similar thing for if n is equal to 1, for instance? So let's try n is equal to 1. In this case, we have just 2n plus 1 is equal to 3. We have 3 sets. A1, A2, A3, it would be, let's try. So for instance, if I color this one as yellow, the other one emanating from A1 should be green. But now I'm stuck, because if I can't color this. If I color it green, then it means A2 has two greens in it. If I color it yellow, then A3 will have two yellows in it coming out of it, two edges. So that won't work. So this case is definitely failing. So this case doesn't work. We know that n is equal to 2 works. How about n equals 3? N equals 3 would suggest 2n plus 1 is equal to 2 times 3 plus 1, which is 7. Yeah, so let's try that. So let me draw a circle, I guess. So the vertex is here, like that. Okay, so we have this polygon and all of its diagonals, obviously, so many of them. Okay, and we need to think of a way to color all these vertices such that such that from each vertex we will have an equal number of colors emanating, right? So as you can see, from each vertex we have 1, 2, 3, 4, 5, 6 lines coming out. 1, 2, 3, 4, 5, 6, and so on. 1, 2, 3, 4. Yeah. So this one is missing one. Yeah, this one is missing. Sorry for that. 1, 2, 3, 4, 5. So we are missing one. Which one is missing? 1, 2, 3, 4, 5, 6. Sorry. Yeah, it's all. This one is again will become challenging. There is no clear way of doing this. So how to do it? Well, before I begin then, so let's be smart in here. So this is A1, A2, A3, A4, A5, A6, A7. After some trial and error, you realize that this case might not work actually, and in fact it doesn't. And the reason is that if you count, for instance, how many lines are emanating coming out of A1, we have 2n lines coming out, going to all the other 2n vertices, subsets, right? A half of them has to be one color and the other half the other color. So therefore, so the number of the total number of lines in this whole picture is equal to basically well, 2n plus 1. So let's write that down. 2n plus 1 choose 2, right? Which is simply equal to 2n plus 1 times 2n over 2, which is equal to 2n plus 1 times n. So this is the total number of lines. So this is the total number of lines. So this is the total number of lines. So half of it, 2n plus 1 over n over times n over 2. So that must be an integer, right? It must be an integer because so this is total number of lines. Half of these lines by symmetry must be one color and the other half must be the other color. So therefore this number should be an integer. But look, inside is always an odd number. So therefore this implies n has to be an even number. So no wonder it's impossible to do this task with whenever n is odd. So first of all, this establishes that n has to be even. But once it's even, so for instance, we were able to luckily solve this one. So this was obviously n equals 1 wouldn't work from the beginning. N equals 3 the same. So we don't have to check the odd numbers again. But n equals 2 worked, right? So how can we make it work for other cases? For instance, let's try one more case to see if we can constructively build something. So when n is equal to 4, 2n plus 1 is equal to 9. So we have a 9 gone. So let me draw my circle, and on that circle, 9, there you go. Okay, so that should be a 9 gone. There are too many lines in this picture. So what I will do is I will come up with the following. So okay, so you can pause the video here and you can try to see if you can come up with all the vertices, all the edges. 9 choose 2 edges here. 9 times 8 over 2, 36 edges. It's 18 of them one color and the other 18 of the other color. In my case, I will draw the colors red and blue now. Let's see if I should be able to find a scheme where to add 18 blue and 18 red colors such that an equal number, for instance, from each vertex, our understanding is that there will be 8 lines coming out of this, right? 4 of them should be red, 4 of them blue. So here is the construction. Okay, first draw the edges one color. So these points, so these lines just join adjacent vertices. Now step 2, switch the color and then skip one vertex and draw the line connecting them in the other color. So that's blue, and so on. Blue, 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 and blue. Now step 3, in the third layer of coloring, we go back to the red color. Now we will skip 2 vertices, like that. 1, 2, 3, 4, 5, 6, 7, 8, and 8. Wait a second. 8, yeah, and 9. Okay. And finally, one more layer. This time we will skip 1, 2, 3 adjacent points, but we go back to the blue color. Skip 3. 1, 2, 3. So we go to that one. 1. This one, 2, 3. Okay, so does that make sense? 4, 5, 6, 7. Okay, so it's already pretty messy picture now. 8. Oh, 8. Okay, I skipped 3. 9. And that's it. Whew. Okay, so we're in for quite a show here, right? So 2, 3, 4, 5, 6, 7, 8, 9. So during the first layer, during the first layer, we used 9 red lines. So therefore, and in the second layer, we used 9 blue lines. Blue. Third layer, we used 9 red lines again. And finally, during the fourth layer, we used 9 blue lines again. So in the overall picture, we have 36 lines, and obviously this counts to 36 as well. So we colored all the lines and in an equal number of ways. So we have 9 plus 9, 18 red lines, and again 9 blue lines plus 9 blue lines for a total of 18 blue lines. So that's clear. Okay, so I will go ahead and erase this. So let's count how many red and blue comes out of point 1. 4 red, 4 blue. And the same thing for point 2, vertex 2. So this is associated, remember, with the subset A1, A2, A3, and so on, right? So you have 4 red and 4 blue. That works. And 4 red. So does that make sense? So this coloring scheme should work because this even layer of points, right? So you have an even, so for instance, when you have 9 points, we did 4 rounds. 2 rounds of reds and 2 rounds of blue. The same thing here. When n is equal to 2, we had 2 rounds of coloring, 1 round of yellow and 1 round of green. And so therefore the coloring matched perfectly. So obviously you can, this scheme works, so but I will not write a formal description. But what you can do is you can come up with a function, or let me actually write the function and then I leave it to you to prove it. So the function that works for that solves the problem, so you can define a function f from the set B to the number 0, 1. So it takes the elements of our set B and it assigns numbers 0 and 1. So so it is basically a generalization of what we did here, or kind of an abstraction of what we did here. And if you define the formula like this, that should work. So f of x is equal to 1 if x is in AI intersection AJ, where j minus I is simply in the following set: 2, 4, n. Remember, n was an even number. Union n plus 1, n plus 3, n 2n minus 1, 2n minus 1. And it is equal to 0 if x is in, again, AI intersection AJ, where j minus I, when I say j minus I, you understand that it's how many elements I'm skipping, right? So for instance, A1, A2 minus A1, they are adjacent subsets. So I decided to color it red. So the red here is associated, because the difference is 1, it would have been a 0. So the red here is actually the number 0, if you will. But anyhow, so let's go back to this. So that's 1, 3, n minus 1, union n plus 2 all the way to 2n. Well, obviously going even in even increments, so n plus 2, n plus 4, and all the way to 2n. Therefore, to conclude, let's summarize everything here. We can say that 1 can assign to each b in B 1 of 0 or 1, such that the condition such that each AI has equal 0 and 1 assigned to its elements, if and only if n is even. So that's kind of the conclusion, and we created a construction, namely this one, that clearly for any given even n satisfies the given condition of the problem. So that solves this beautiful problem. It felt like it wasn't really a number 2, but rather a number 3 or a number 6 for that year, for the year 1988. But that's all. Hope you enjoyed the video, and looking forward to see you guys in our next lecture.